I love the beach. Early one morning 2 months ago, I was lucky enough to be standing on Bondi Beach in Sydney. And as I looked down at my feet, I saw not only the golden sand between my toes, but also technology's bedrock. Because as The Economist put it, technology is built on sand. It is not commonly known that computer chips are in fact built from refined sand, starting in a form much like the sand on our beaches. These computer chips hold millions of transistors, tiny electrical switches, and the density of these transistors has been roughly doubling every 2 years since the 1960s. So much so that modern smartphones are now more powerful than the Apollo space computers that put man on the moon. However, these transistors, now only tens of atoms wide, cannot continue to shrink. We have to find new and innovative ways in which to improve computational processing. One such proposal is a quantum computer. A quantum computer is a computer that exploits the weirdness of quantum mechanics to process information. Quantum mechanics are properties that are inherent to all atoms, and at the moment, though very complex, are a powerful and untapped resource. Modern computer chips and computer bits, which represent binary information, can exist in two states, much like a light globe. They can be on or off, or in a binary state 1 or 0. The beauty of quantum bits, or qubits, is that they can be on and off at the same time. What entities can we use to represent these bits? Well, we can use, for example, the intrinsic spin of an electron. Much like a spinning top, it spins on its own axis, and that spin direction is represented by this arrow that I've drawn through the electron here. And so we can have a spin up or a spin down electron corresponding to whether it's spinning this way or the other way. And these spin directions correspond to these classical binary 1 and 0 states that I was talking about. And like all quantum bits, they can exist in that superposition, both a 1 and 0 at the same time, as you can see down the bottom. But how do we manipulate these spins? Well, that's where the spin doctoring comes in. And no, I'm not talking about putting a positive spin on bad news. I'm talking about doctoring the spin state of an electron. And we do that, yep, you guessed it, with magnets. Sweetly tuned, glorious magnetic fields. And so how do we relate this back to silicon? Well, if we dope our silicon with just a small amount of, say, the element phosphorus, whose outer electron and nucleus both have an intrinsic spin, we now have a lattice of qubits to build our quantum computer. The beauty of this architecture is that we use the existing technology that we've used to build computer chips over the last 50 years, which also means we get to exploit the 50 years of fabrication techniques that we've been using to make these computer chips. What's more, silicon happens to be an ideal environment with which to host these spins. So where are we at? We've got these computer chips that host millions of transistors, and these transistors are so ubiquitous that there's probably about 1 billion in most people's pockets today. We also have this idea that there's a quantum computer that could perhaps process information exponentially faster than a modern computer. It must be said, however, that quantum computers can only process very specific, though very useful, algorithms. One such example is, if we consider something that's going to be spoken about later today, big data. Quantum computers will be exponentially faster at searching databases or bringing clarity from an overload or mess of information. Another proposed problem that can be addressed is the traveling salesman problem. This idea that we want to try and minimize the distance a salesman has to travel between a number of pre-selected destinations. Although it sounds trivial, the problem gets exponentially more difficult, and quantum computers will be great at optimizing it. It will be very useful to logistics companies. This idea of a quantum computer is definitely not a pipe dream. Research groups around the world are trying to build one. And it just so happens that the silicon spin architecture that I've been speaking about is one of the world-leading candidates. And the driver of that technology, research done at this centre, the Quantum Centre at the University of New South Wales in Sydney. It so happens that the federal government, together with the Commonwealth Bank, a proud supporter of the Monash Foundation, and Telstra have recently invested a total of $46 million into UNSW to try and build the first quantum computer. But what does that mean for Australia and its future? Well, at the very fundamental level, investment in scientific research and graduate students has been shown to provide a significant annualized return to the domestic economy. But why invest in quantum computing? What's the advantage? Well, the idea is it can create a completely new industry, an industry that will result in spin-out companies, intellectual property, and the development of centres of excellence. And this will attract further intellectual investment and tie in well into the innovative ecosystem that the federal government has been promoting as part of its innovation agenda. And this will all be fed by the research and ideas and technology coming out of the University of New South Wales. Where will this occur? Well, the Australian Technology Park in the southern part of the city centre is something that's been developed by both public and private companies, as well as Silicon Harbour, which is at the old White Bay Power Station, is a site that's been set up by the New South Wales government to try and drive this change and host technology companies. So, next time you're standing on the beach, I want you to look down at the sand and remember that you're standing on the bedrock of the digital age, silicon. Before I leave, I want to leave you with one last thought. Several years ago, 3 children in Melbourne were asked by a newspaper, how can they make Melbourne a better place? The key answer, more magnets. And I think this idea can apply nationally, if not internationally, because if we're going to have a quantum computing industry, we're going to need many, many more magnets.